Morning, students. Myself, Vijay Shankar from EC Department, Chevrolet Engineering College. Today, we are going to discuss about the multiplexer and de-multiplexer, the design of multiplexer and the de-multiplexer. In the yesterday class, also a brief description about the multiplexer is also be discussed. And in the today's class, also we start from the multiplexer from basic 2x1 multiplexer and the 4x1 multiplexer and so on. And the de-multiplexer also, how we can design the higher multiplexer to the by using the lower de-multiplexer. Okay. The multiplexer. Multiplexer. Yesterday we already started this one. It's a basic 2-input multiplexer. Basic 2-input multiplexer. Following. So 2-input multiplexer means 2 power n number of inputs in the multiplexer and n number of selection lines and one output line. The 2 power n means n is here is a 1 selection line is there, the 2 inputs and one output. The 2 inputs are D0 and the D1, and S is the selection line and Z is the output. So when I am selecting the S is equal to 0 here, in the Z, whatever the D0 having the data, that will appear on the Z at the output. And when I am selecting the S is equal to 1, whatever the data in the input D1, that data will get in the output Z is equal to. Okay. Using this truth table, the Z Boolean expression is S bar. This S is equal to 0. This S is equal to 0. S bar D0 plus S D1. S is equal to 1 and the D1 means S D1 plus S bar D0. Okay, using this Boolean function, the logical diagram will get like this with the 2 AND gates and 1 OR gate, 1 inverter. That is inverter for S. When S is equal to 0, when S is equal to 0, we'll get as inverter output is 1 and the D0. So first AND gate is enable and second AND gate is a disable. Then we'll get the Z is equal to D0 only. And when S is equal to 1, S is equal to 1 means the inverter output is a 0 here. Inverter output is a 0. And first AND gate 1 is disable and AND gate 2 is enable. Okay. Like that we'll get when S is equal to a selection line, S is equal to 0 and S is equal to 1. See here, when S is equal to 0, AND gate 1 is enable and AND gate 2 is disable. So Z is equal to D0. Okay, whatever the data in the D0, the first input will get in the output side. When S is equal to 1, AND gate 2 is enabled, AND gate 2 is enabled, and AND gate 1 is disabled because of S is equal to 1, the inverter output is 0. One of the input of AND gate is 0 means the output is also 0. Okay, so the AND gate 1 is disabled, AND gate 1 is disabled, AND gate 2 is enabled. Then the output Z is equal to the D1, whatever the data is there in the D1, that will get in the output side. Okay. Now you can see the next one is a basic 4-input multiplexer. 4-input multiplexer means 2 power 2. The 4 inputs means in the powers, the 2 powers 2 square. 2 square means n number of selection lines are there. Here the 2. The 2 selection lines will get as an input of 4x1 MUX. The 2 input selection inputs are S1 and S0. S1 and S0 and 4 inputs. The 4 inputs are D0, D1, D2 and D3. Okay. The multiplexer having only the one output. Output is a Z. Now here the 2 selection lines means the binary equivalence of the 2 bit is 0, 0, 0, 1, 1, 0 and 1, 1 conditions. So when I am selecting S is equal to 0 and S1 is equal to 0, the first input, whatever the first input is, the D0 will get in the output side, will appear in the output side. The second option is when I am selecting S is equal to 0, S1 is equal to 0, S0 is equal to 1. Means the decimal value of 1, it is a binary equivalence is 0, 1. So when I am selecting these two selection lines as 1, S0 is 1 and S1 is 0, the D1 will get in the output side. And S is equal to 0, S0 is equal to 0, S1 is equal to 1, means the decimal value is a 2. So it selects, when I am selecting the two values of 1, 0, the D2 will get in the output side. D2 will get in the output side. Okay. And now the last, it is a 1, 1. 1, 1 means that is a binary of decimal 3. Binary of decimal 3. So when I am selecting the S0 and S1 is both are ones, that whatever the data is there in the D3 or whatever the value is there in the D3, that will appear at the output side. Means data selector. The another name of the multiplexer is a data selector. Okay. Next step. See we will get the truth table. Now we have to write the Boolean expression of the Z. What is the Boolean expression of the Z? These 3 is a product here, the first 3. So S0 is 0, S1 is a 0, and D0. Okay, S0 is a 0, S1 is a 0, and the D0. And I am saying and is a product. So S0 bar, S1 bar, and D0. Following my students, plus the second option here we'll get the second option. Zero and 1 means S0 is 1. So see whatever it is okay. S0 is 1. So S0, it is uncomplement value. S1 is a 0. S1 is a 0. So S1 bar and the D1 plus the next option is S0 is a 0 and S1 is a 1. So S0 bar S1 into D2. Okay, my dear students. Now, wherever it is a 1 is there, it is uncomplement value. Wherever it is a 0 is there, it is a complement value. And the last term is S0 is 1 and S1 is also 1. So S0, S1 into D3. S0, S1 into D3. All right. That is a Boolean function we got for the Z is equal to. Z is equal to. So by using this equation, you have to go to draw the logical diagram. You see the logical diagram here. Having S0 and S1, S0 and S1, and the S0 bar and the S1 bar by using this inverter. Totally we have the 4 lines you have to draw vertically. You see the first term means that the 4 AND gates are required because of the 4 terms are there in the Z. The first AND gate input the 3 inputs. One is a D0. Another 2 inputs see here. The first term is S0 bar and S1 bar. So S0 bar means the inverter from the inverter and S1 bar here. So these 2 inputs are connected to the first AND gate. And second AND gate is there, having the 3 inputs are there. The one input is already the D1. Another 2 inputs is S0 and S1 bar. You see S0, the 4th line from the 4th line connected, and S1 bar, that is the first line. Okay. Next, third term it is it is also 3 input AND gate. One input is a D2. Another 2 inputs are from the selection lines. S0 bar is a third line, and S1, it is a second line. Okay, from the second line you can connect as a 2 inputs of the third AND gate. Following. And the 4th AND gate is there. For the 4th AND gate is also the 3 input. One input is a D3 and another 2 inputs are S0 and S1. The second from the second line and the 4th line you have to connect as a 2 inputs of the AND gate. As a 2 inputs of the AND gate. Okay. Then all these outputs, all the 4 AND gates output is connected to the OR gate because of all the terms is added here, product terms. So that is a Z. Z is equal to S0 bar, S1 bar, D0 plus S0, S1 bar, D1 plus S0 bar, S1, D2 plus S0, S1, D3. Okay, the logical diagram will get from the Boolean function. That Boolean function will get from the truth table. And the truth table will get from the block diagram of the 4x1 multiplexer. So the 4x1 multiplexer, whenever there is a selection lines, you can select the data according to the selection lines. The data will get at the input 0 0. Why? We can ask that one question also. Why it is a D0 when I am selecting the 0 0 only? Why it is not the D3? We can also D3. We can give that D3 also. That is not the wrong, but the designing is different. Designing is different. When I am selecting the 0 0, it is a D3. 0 1, it is a D2. 1 0 is a D1. 1 1 is a D0. Like that also you can design the circuit according to the Boolean function only. The logical diagram will change. Okay, so 0 0 will get the D3, 0 1 D2, 1 0 D1, and 1 1 the D0 will get. But default every time we are taking that is a 0 0 is a 0 only, the D0 will get. And 0 1 is a 1 is a decimal value, so D1 will get at the output side. And 1 0 the decimal value is a 2, so the D2 is get at the output side. And 1 1 is a 3 of the decimal value, so D3 will get. Like that it is there is no any ambiguity. Following my dear students, it is a mandatory. Otherwise you can do whatever it is a design. You can take the 0 0 as a D3, 0 1 is a D2, and 1 0 is a D1, and 1 1 is also D0. Okay, the change of the Boolean function. According to the Boolean function, the logical diagram will change. Alright. Then the next one is the similar way the 8 input multiplexer also. See, we have the 2x1 multiplexer and 8x1 multiplexer, 4x1 multiplexer we see. Now I can draw the 8x1 multiplexer. 8x1 multiplexer. Let us see here. 8x1 MUX. So 8, that is a representation of by 8x1 MUX. The shortcut notation of the multiplexer is 8 MUX. So first input is a D0, and 8 inputs means totally the D0 to D7. D0 to D7. Okay. And 8 is nothing but the 2 power 3. 2 power 3 by 1. Okay. 2 power 3 by 1. 3 is a selection lines. What is the selection lines here? The 3 selection lines are there. The 3 selection lines are, one is S2 and another is S1 and the S0. So in between there is a D1 is there, D2, D3 and D4, D5 and so on up to D7. So only it's having the one input, one output, not the output. Sorry, it is Z is output. Well, this is the block diagram of the 8x1 MUX. Now the truth table is S2, S1 and S0. So there is a 3-bit binary. 3-bit binary. That is a 3-bit binary is a 0 0, 0 0 1 and 0 1 0 and 0 1 1 as a 3, 1 0 0 and 1 0 1 and 1 1 0 and 1 1 1. This is a 3-bit binary. So because we have the 3 selection lines are there, and output Z is equal. What is output Z now? When I am selecting the 0 0 0, the D0 will appear at the output side, and 0 0 1, the D1 will appear at the output side, and 0 1 0, the D2 will get, and 0 1 1 at output side we get D3 data, and next it is a D4 data we'll get when the selection lines here, And another one is there, the D5, when I'm selecting 101. And when I'm selecting 110, the D6 will appear at the output side. And when I'm selecting the 111, the D7 will appear at the output side. Okay, my dear students. So now using this truth table, how to write the Boolean function. What is a Boolean function? That Z is equal to the first three here. See, this one. So S0 is 0, S1 is 0, S2 is 0. Means S0 bar, S1 bar, and S2 bar, because all it is a 0, and the D0. Okay, and the D0. And next one is a plus. See the second one. So S0 is 1. S0 is 1 means S0 uncomplement value. S1 and S2 is both are the two zeros. So S1 bar, S2 bar, and D1. Okay. So to design here these product values, it requires AND gate with 4 input AND gates. Plus, next one is the third one, you can see here. Third, S0 is 0, S1 is 1, and S2 is 0. So S0 bar, S1, and S2 bar, and output is a D2. The product. Plus, the next fourth one here. You can see the fourth one. 0, 1, 1. 0, 1, 1 means S0 is 1, so S0. S1 is 1, so S1. And S2 is a 0, it is a complement value. S2 bar, and the D3. Okay. And next one is fifth one, plus 100. 100 means S0 is complement value. S1 is also complement value, and the S2 is the D4. Okay, 0100 it is. So plus, again you can see here the D5. So S0 is 1, so S0. S1 is 0, S1 bar, and S2 is 1, so S2, and the D5. Okay. And seventh one you can see 110. 110 means S0 is a 0, so S0 bar, S1, S2, and the D6. Okay, and D6. And the last one you can see the last term in the Boolean function, the Z is equal to, it is S0, S1, and the S2, D7. So like that, from the truth table, you have to write the Boolean function Z is equal to. For 2 by 1 MUX, it having only the 2 terms. And 3 by 1 MUX, 4 by 1 MUX, it having the 4. And now you get here 8. 8 terms are there. 8 terms with 3 selection lines. Okay. 2 by 1 MUX means the 2 terms will get in the Z. And 4 by 1 MUX will for the 4. And 8 by 1 MUX will get the Z is equal to 8 terms. 8 terms. Okay. Now let us see here how we can draw the logical diagram. Now, first I am taking S0 and use the inverter here. Inverter, S0 bar it is. S0 bar. And now taking the S1. Take that is S1 here. And S0, S1 bar using the inverter. Okay. The next S2. Take that one line, vertical line, and the inverter S2 bar. Okay. So totally the 6 vertical lines it is required to draw a logical diagram from the by using the Boolean function. Okay. First I am taking the AND gate. The first AND gate. Let us see the AND gate. It requires 4 inputs. Okay. What is the 4 inputs? So one input is D0. Another input is S0 bar. So see here, I am connecting from the S0 bar. Okay. And S1 bar. And another one is S2 bar. Okay. So like that, the first AND gate will get. The second AND gate. The second AND gate, the output. One of the input is a D1. One of the input is a D1. So see what is the second equation, S0, S1 bar and S2 bar. So the two are complement value, S0 is uncomplement value. Let us see, S0 is uncomplement value. So directly I am connecting from here, S0 and S1 bar and S2 bar. S1 bar and the S2 bar. Okay. That is the second AND gate output. So D0, not the D0, say it is a D1, S0, S1 bar and the S2 bar. So like that, you can use all the AND gates according to our Boolean function. And the last Boolean function you can see here, S0, S1, S2 and D7. S0, S1 and D7. Okay. You see S0. Now I am drawing the last one, S0, S1 and S2. All it is a ones. And another input is there, that is a D7. D7 connected to the OR gate, AND gate. Now all the outputs, whatever you are getting, the D and so on here, connected to the OR gate. To get the output, Z is equal to. So like that, we can draw the logical diagram of the 8x1 MUX. So we already seen the 2x1 MUX, and it requires a 2 AND gates, 1 inverter and 1 OR gate. And 4x1 MUX we already seen, 4 AND gates, 2 inverters and 1 OR gate. And the 8x1 MUX, the 8x1 MUX, it requires 8 AND gates, 1 OR gate and 3 inverters. 3 inverters. Following my dear students. And now let us see how you can design the 16 input multiplexer from 2 8 input multiplexers. So we already seen the 8 input multiplexer. By using this 8 input multiplexer, you can design the 16 by 1 multiplexer. You see, to use 2 input multiplexers to get a 16 input multiplexer. So definitely the 2 8 input multiplexers means the first 8 by 1 multiplexer having the D0 to D7. Totally 8 inputs are there. And the second 8 by 1 MUX having again the D0 to D7, 8 inputs are there. But for designing of 16 input multiplexer, you can start from the D0 to D7 for the first 8 by 1 multiplexer. And for the second 8 by 1 multiplexer, you can start from the D8 to D50. So totally the 16 inputs is okay. And multiplexer having only the one output. So from 8 by 1 MUX, there is a one output is there. And another one is there. Second 8 by 1 multiplexer also another output. So you can combine these two and connect it to the OR gate, we'll get the one output. That is also okay. So what about the selection lines? For 8 by 1 multiplexer, there is a 3 selection lines are there. But to design the 16 by 1 input multiplexer, it requires 4 selection lines because it's a 2 power 4 is the inputs. 2 power 4 is a 16 inputs. So 4 selection lines are required. Already the first 8 by 1 multiplexer having the 2, 3 and second 8 by 1 mux is also having the 3 is there. Okay, what about the fourth one? We can combine these three for the first and the second one. You'll get the 3 inputs, so 3 selection lines are there. Another input you have to require, that is a fourth input. All right, let us see how we can draw this one. So the 16 input multiplexer or 1 OR gate and 1 inverter are also required. See, not only the 2 8 input multiplexer to get a 16 input multiplexer, 1 OR gate and 1 inverter also required. What is a 1 OR gate? Combining of the 2 outputs connected as a single output. And 1 inverter also is required. 1 inverter means, see, there is an inbuilt of multiplexer. There is an inverter. You can use enable input, simply you can say. Enable input using the inverter. There is enable input is a inbuilt of the multiplexer. You can use that enable input connected to the inverter. One time the first 8 by 1 multiplexer is enable and second 8 by 1 multiplexer is a disable. A disable means all the outputs is a 0 simply. Even if the selection lines is selecting also, the output is a 0. Alright. And another time, 1 multiplexer, above multiplexer, 8 by 1 multiplexer is disable and below 8 by 1 multiplexer is a enable. Then we'll get according to the selection lines. Let us see that also. The 4 selected inputs, I'm taking here the 4 selected inputs are S0, S1, S2 and S3. And we'll select one of the 16 inputs, to pass through the X. Pass through to X value. So the S3 input determines which multiplexer is enabled. S3, the last one. I am taking the S0, S1, S2 or the 3 selection lines from the 8 by 1 multiplexer. Additionally, I am using the 1 OR gate to get the output as a combined value. And another inverter is there. That inverter is connected to the S3. The S3 input determines the multiplexer is, which multiplexer is enabled. So whenever it is an inverter is there, I am connecting the 0. Inverter output is a 1. 1 will get for the enable input. So first 8 by 1 multiplexer is enabled. Let us see when S is equal to 0. S is equal to 0. The left multiplexer. You see in the left multiplexer means here the design is already there. This is a left. And this one is a right. It's lower order multiplexer and higher order multiplexer. Following my students. Higher order means it is a 0 to 7 I represented here and 8 to 15. So it is a higher order and this one is a lower order. Meanwhile, you can assume this is the left side and this is the right side. In the left enable, when S3 is equal to 0, the left multiplexer is enable. Left multiplexer is enable. And S2, S1 and S0 inputs determines which of its data inputs will be appear at its output. So now, whenever if it is the left input is enable, left input is enable means the second right multiplexer is disable. Disable means all the higher orders is a 0 then. Only when I am selecting the S0, S1, S2 is equal to 0, 0, D0 will appear here. D0, and because of this is a disable, the second one, here will get the 0. Okay. The one of the input of the OR gate is a 0 here. So second I am selecting the 0, 0, 1. 0, 0, 1. 0, 0, 1 means D1 is get at the output side here. So D1. So what is here the another input of the OR gate? It is a 0. Again, you will get the output is a D2, D1 only. Then after selecting of a 0, 0, 1, whatever we discussed earlier, that is here, see according to this one. So according to the 0, 0, D0 will get the 0, 0, 1, D1 is get 0, 1, 0, it is a D2, and so on 1, 1, 1, D7 will appear at the output side. Whenever the S3 is equal to 0. S3 is equal to 0, my dear students. Okay. Now suppose when S3 is equal to 1, the second case, when S3 is equal to 1, the right multiplexer is enabled. The right multiplexer means higher order multiplexer here, enabled, and the lower order multiplexer left side it is a disabled. Disable means all the outputs here it is output is a 1 is there, it is a 0 only for every case. Even if it is S0, S1, S2 is a 0, 0, 0, will not get at the T0 because this enable input is a 0 here. Enable input is a 0. Because of this 0, the lower order multiplexer or the left hand side multiplexer is a disable. Always it is a 0 for 8 options. Okay. Now the second right hand side multiplexer is enabled, that is nothing but higher order. Now according to the S0, S1, S2, S3. So enabled and S2, S1, S0 inputs select one of its data inputs for passage to output X. Here I am taking the X here, or it is a Z also. So now I am selecting the S0, S1, S2 is a 0, 0, 0. Now what you have to select here? D8. You see here the higher order. Whatever the first input is there here, that will appear at the output side. That is a D0, not the D0, it is a D8. And the second input is of the OR gate is a 0 because it is enable. Disable, not the enable, sorry. It is a disable. And 0, 0, 1, D9 will appear here. And 0, 1, 0, D10 will appear here. And 0, 1, 1, D11 will appear. Understood, my dear students? But otherwise, you can see, I will draw the in simple way. See, 1, 8 by 1 MUX here. 8 by 1 MUX. Another 8 by 1 MUX I am taking here. 8 by 1 MUX. And here for these two outputs, and the two outputs will get. Combine these two outputs as an OR gate. And Z is output. Okay. And now I am writing the D0 here. And D7 is here. So totally 8 inputs. And second 8 by 1 multiplexer, I am writing here it is a direct, it is a D8. D8 to D15. So 0 to 15, totally 16 inputs. Okay. Now there is 3 selection lines only. The 3 selection lines are S0, S1, and the S2. And here also there is a S0, S1, and the S2 is there. Following. I'm combining these functions. You see here. I'm combining S0 as a red line. And another one I am combining S2, S1, not S2. S1 is with another color. And the last one is there. I am connecting like this. Okay. So it is a S0, S1, S0, S1, and the S0, S2. Okay. And similarly here also S0, S1, and the S0. Now what is the truth table here saying? S3, S2, S1, and the S0. Starting it is a 0, 0, 0. It's a binary. Up to the 7. 0, 1, 1, 1 will get. Okay. You see, these are up to S3 is 0. So S3 is equal to 0. The first 8 by 1 multiplexer is enabled. And second case 8. The binary of 8 is 0, 0, 0 like this. Okay, 1, 0, 0, 1. So same options 0, 0, 1. But up to the 0 to 7, the S3 is 0. And from 8 to 9, the S3 is 1. But the remaining is the same 1, 1, 1, and 1. So on here. Following. Whenever the S3, if I am connecting the S3 is here with inverter as another input, as an enable input, you connect it to the enable input here, and S3. I'm connecting here as a S3. So this is a S3. Okay. So when it is S3 is equal to 0, S3 is equal to 0 with this inverter, we'll get the 1. So it is enable. Enable when S3 is equal to 0. And this is a disable, and below it is a disable when S3 is equal to 0. S3 is equal to 0. Following my dear students, S3 is equal to 0 means it is always, its output is a 0 only. In this condition, always this output is a 0. And here the output is depends upon the S0 and S1. Now when I am selecting the S3 is equal to 1 here, S3 is equal to 1, and this one is a disable now. Disable. The first one is a disable. The output is always a 0 here in this condition. This condition is 0. And now here it is enable. When it is when S3 is equal to 1. When S3 is equal to 1, the second 8x1 MUX is the enable. Okay. When it is an enable, the values is totally it is a zeros. Only whatever the output will get here from D0 to D7. Go on, it is increases D0 to D7. Whenever the S3 is equal to 1, whenever it is a 1 means this is enable, and the first 8x1 multiplexer is a disable. So at this disable condition, all the values is 0 here. Now it is enable means D8 will appear here, D9 will appear here, and up to so on. D15 will appear at the Z. Following my dear students, this is a block diagram only. This is a block diagram only. If coming to the Boolean expression, what is the Boolean expression? We'll get Z is equal to, so S0 bar, S1 bar, S2 bar, and the S3 bar D0. As usual, whatever the equations are there, the 4 selection lines are there. So previously S0, S1, S2 bars. Next 0, 0, 0, 1. 0, 0, 1 means 0, S0 bar, S1 bar, and so on, and go on. It is a D1 plus D2 plus D3. Like that, we'll get the 16 terms for the Z. 16 terms for the Z. 16 terms means the logical function required the 16 AND gates with 4 input AND gates. The 4 input 16 AND gates and 1 OR gate combining of all the 16s. And how many number of inverters required? Because of 4 selection lines are there, 4 inverters required. So to design the logical diagram or to draw the logical diagram of 16x1 MUX, the same thing, 16x1 MUX, it requires 4 inverters and 16 AND gates of 4 input and 16 input OR gate. 16 input OR gate, simply. Following my students, like that we can design 16x1 MUX by using the 2 8x1 MUX. What is the additional logical gates is required here? The 2 8x1 MUX and 1 OR gate and 1 inverter. Okay, that only here is explained in the theory. You see, to use the 16x1 multiplexer from 2 8x1 multiplexer, to use 2 8 input multiplexers to get a 16 input multiplexer and 1 OR gate and 1 inverter also required. 1 OR gate and 1 inverter also is required. That only here. 1 inverter here. See, the inverter is there. That inverter output is connected to the one of the enable input is a inbuilt. There is an enable input is there that we can use whenever higher order multiplexer is designed by using the lower order multiplexers. Means the 16. See, to design here to obtain the 1x32 demultiplexer using a 1x16 demultiplexer, a 32 outputs, so it requires 5 data selector lines. Since 1x16 demultiplexer has only the 4 selected inputs, that is a B, C, D, E are connected to the data selected lines of both the 1/16 demultiplexer, and the most significant input A is the most significant bit A is, see here, I use the most significant bit A. E is the least significant bit and A is the most significant bit. It's MSB, and this is a MSB, and this one is a LSB. Okay, the most significant bit is input is A, connected to the single data selector line of both 1/16 demultiplexer enable input. 1 demultiplexer enable input. But here you see enable is a bar. So I am taking here the enable is a bar, means I'm selecting the 0, and this 0 with this 0 it is an enable, and I am selecting the 0 here 1, and 1 means with this bubble it is a disable. Okay, when I'm selecting A is equal to 0, A is equal to 0, the inverter output is a 1, and 1 with this bubble there is a 0. So second 1/16 demultiplexer is disable, and when I'm selecting A is equal to 1, A is equal to 1 with this bubble, the first 1/16 demultiplexer is disable, 1 is there with our inverter output is a 0 with this 0 and this bubble here. Okay, is a complement value. Enable is a complement value. So 0 and 0, this is a enable value. Following my dear students. You see the enable bar, EN bar input. The 1 to 16 will appear in the first demultiplexer when A is equal to 0. You see here, when A is equal to 0, 1 to 16, it is not the 1 to 16, it is a 0 to 15. Will appear in the first demultiplexer, and 16 to 31 will appear in the second demultiplexer when A is equal to 1. When A is equal to 1, because of taking off the enable input is complement enable input. When A is equal to 0, the first 1/16 demultiplexer is enable, and second 1/16 demultiplexer is a disable. And next another time when I am taking the A is equal to 1, the first 1/16 demultiplexer is disable, and the second 1/16 demultiplexer is enable. Okay, my dear students. So with this, you'll get completing of the higher order demultiplexer is designed by using the lower order demultiplexer. Fine. Now let us see, if suppose if they ask design the 1/8 demultiplexer using 1/8 demultiplexer using 1/4 demultiplexer. Okay, 1/4 DMUX. Let us see how we can design this one. I'm taking the 1/4 demultiplexer. It's having 4 outputs. That is from O0 to O3. Okay, it is a O1 and it is a O2. And having 2 selection lines are there. That 2 selection lines, one is a B and another one is a C. And similarly for this also, 1/4 demultiplexer, the outputs are, now I am taking the second one is connected as a O4, O5, the outputs, and a O6 and the O7. Okay, and it is also having 2 selection lines. It also having the 2 selection lines. That is, one is a B, another one is a C. So B is connected. Now I am using this B is connected here, and C is connected here. Okay, C is this one. Is a C. So what is another input? That is a B value, and this one is a C. So 1/8 demultiplexer means that the selection lines are A, B, and the C. Okay, and outputs are from O0 to O7, O0 to O7. Following, A is 0 here. When I'm changing that 0 0 to 1 1 1, it is a one option here. Another one 1 0 0. Okay, and these are up to 0 1 1 1. So in this case, when I'm selecting the A is equal to 0, A is equal to 0 means the first one. Let us, I'm taking the A is here. Using this one inverter here, I'm connecting as of one enable input. Enable input. Okay. And the A is connected here, another enable input. So if A is a 0 means that is a enable bar, and here also it is enable bar. When A is equal to 0, with this 0 and this bubble, the first 1/4 demultiplexer is enabled. When A is equal to 0, the output of an inverter is a 0, and 0 it becomes of 1, and it's not the 1, it's a 0, it's not the 0, my dear students. It's wrong. When A is equal to 0, the value is 1, and 1 with bubble, it is a disable. Means O0 to O4 to O7 is a disable until the total 5 options from 0 0 to 0 1 1 1. 0 1 2 3. So total is a 4. When I am connecting these as A is equal to 1, A is equal to 1 means directly you get this is a bubble and this one is a disable, and A is equal to 1, it becomes of the 0, and now the lower 1/4 demultiplexer is enabled. Lower 1/4 demultiplexer is enabled. So like